Now we'll talk about one more type of hazards, control hazards. In control hazards, so we will be having branch instructions, okay? Because of branch instructions, then you get always dilemma whether to take the next instruction or something else, okay? To understand it clearly, first you should understand how this branch instruction is getting executed. Generally what happens if it is not pipelining, then first of all instruction will be fetched, then later in the decode stage we will be understanding that it is branch instruction, then appropriate identifiers will be forwarded to execution stage. In the execution stage R1 and R2 will be compared. Remember one thing, currently program counter value is 100, okay, because we are executing instruction number 1 which is at 100, so program counter shows it. When you fetch this instruction, then automatically in the fetch stage program counter will be incremented to 104. Then after that R1 and R2 will be compared in the execution stage. If they are equal, then effective memory address will be program counter which is 104 plus 50, 154. So effective address is, next address is 154. If R1 not equal to R2, then the next address will be 104. That means we don't update program counter. Understand? So finally in the execution stage we will be finding the effective address which is 154. Now after that in the memory stage we are not going to memory, that's why we keep quiet. In the fifth stage we will be doing writing back. That means the result 154 will be forwarded like this from execution to this buffer. So this write back stage will take that from the buffer and it will write in the appropriate register which is program counter. So program counter value will become 154. So if it is not pipelining, if you do execution one by one, then the next time since program counter is 154, then the fetch is, if the fetch is executed, instruction at 154 will be executed as we expect. Understand? But the story is different here because we are using pipelining. In the pipelining, what generally we were doing, we are simply fetching where whatever the instruction it is, fetch, decode, execute, memory, write back. In the second clock cycle, fetch the second instruction. In the third clock cycle, fetch the next instruction. That way, every time we are fetching a new instruction which is just next to the previous instruction. Correct? Example, the program counter initially at 100. Because of this fetch, it will become 104. Then when you fetch, it will fetch it, this one. In the third clock cycle, this fetch will fetch instruction at 108, because in every stage we are executing fetch, that will increment program counter by 4 so that the next instruction will be executed. That is what the model we were following. But now the story is different because sometimes the next instruction to be fetched is not I2. Here you are executing, or sorry, fetching I2. But that should not happen sometimes, correct? So how to correct it? How to get the right results is a question. To understand that, focus on the first 3 clock cycles. I will tell you the reason, because this instruction execution or execution stage, let us say execution stage. In the execution stage, you will be realizing what is the, whether branch is successful or unsuccessful, correct? Now, so this is the earliest stage you will be getting it, because already I explained you that R1 and R2 will be really compared here. Based on that, effective address will be computed. Let me focus on third clock cycle clearly. In the third clock cycle, on behalf of this instruction number 1, what is going to happen is R1 and R2 will be compared. Assume that R1 and R2 are not equal, okay, just case number 1. Then this regular pipelining model which you are following is absolutely right. Why? I will tell you. First of all, let's fetch the instruction number 1, okay. Now in the second clock cycle, decode it and fetch the next instruction, because when you are fetching here, program counter's value is what? 104. That's why. So what this is fetching now, instruction fetch here will be fetching second instruction, IF2. IF2 means second instruction. There is no problem. Now in the third clock cycle, the first instruction will be, sorry, it is ID1, okay. Now in the third clock cycle, execution 1 will take place. Because of that, what happens? Recall. So because of that, so R1 and R2 will be compared, okay, fine. Then assume that, let's say R1 not equal to R2, so that effective address is 100, simply nothing as usual. That means there is no effective address, correct? So we don't disturb the program counter. Understand? So now after that, you see here at the same time you see the second instruction. What happens to second instruction in the third clock cycle? It will be decoded. Fine. So which one will be decoded? Which is fetched? Since we fetched AND instruction, that will be decoded. So no problem. Then in the third clock cycle, what happens? In the third clock cycle, what happens to this instruction fetch? It will fetch third instruction, because in this level you incremented program counter again, correct? For every fetch, program counter will be incremented. Because of that, for third fetch, 108th instruction will be taken, which is I3. Everything is going good if R1 not equal to R2. Now let us take a case called R1 equal to R2. If R1 equal to R2, then what happens, we'll see. In the execution stage, then the program counter, that means effective address, which is computed by this effective this instruction is, in first one is 154. Okay. Now, then what I want to say is, if really the next instruction is 154, then executing 104th instruction 108 is wrong, but still you are doing here. That is what I would like to say, right? Now, and one more thing, when are you going to really update that program counter? Seriously speaking, in the write back stage we will be updating it, correct? Already I told you. So focus on fifth clock cycle. In the fifth clock cycle, program counter will be updated to 154. By that time, if you see, so second instruction will be fetched, third instruction will be fetched, here fourth instruction also will be fetched, which is here I4. Okay, then here it will be decoding, right? ID4. Now if you carefully observe, when you are writing the program counter result, by that time we will be decoding the fourth instruction, correct? That is absolutely wrong. So executing second instruction, third instruction, fourth instruction, everything is wrong. Then how to rectify it, sir? Very simple. One thing what we can do is, we have to modify our circuit such a way that there should be a detecting circuit. That means, so we should somehow understand that this instruction is branch instruction. We can understand at decode stage. But when are you going to know whether branch is successful or unsuccessful? If branch is unsuccessful, we will be happy. But if branch is successful, then we will not be happy. Okay, so what we do is, in the execution stage, one best thing what we can do is, rather than storing the result of program counter in the write back stage, don't do that. In the earliest, what we can do is, so we will have a circuit, okay, so that will detect control hazards. Okay, how that control hazard circuit works, I will tell you. That you fix in execution stage, so that in the execution stage, whenever the result, because example condition is branch equal. So here in the execution stage, you will be comparing R1 and R2, right? If they are equal, immediately that this hazard should start working. It should say that everything is waste. Okay, immediately there should be a signal. Okay, we can implement it. That signal should flush it. That is called flushing. So finally, this instruction should be flushed, this instruction should be flushed. Try to understand. Okay, this entire instruction should be flushed. However, at which time we can know that? At third clock cycle. So only focus, because this entire thing has not happened so far. Let me erase so that you can clearly understand. At end of the third clock cycle, then by that time you fetched second instruction, decoded, you fetched third instruction, we have to flush them. Flushing means what, sir? Simple. After end of this execution, so better what you do is, in the early stage itself, that means this execution is, you can imagine like one clock cycle, right? In the first half of the clock cycle, you compare very quickly R1 and R2. Comparison takes generally very less time. So compare R1 and R2. Whenever they are equal, then immediately there is a decode stage, right? See, in the third clock cycle, this is the decode stage. So already we have discussed enough. In the decode stage, we will be having, instruction number 2, right? And all the control signals you make zeros. Okay, in the remaining time. Whenever R1 equal to R2, immediately you make all these control signals zeros, and you make all this instruction fetch. Whatever the instruction you fetched, right? You make it 0. Because you will be having one buffer here. What is that buffer? Instruction fetch buffer. Here you will be having instruction decode buffer. In the decode buffer, we will be having what? All the control signals, everything, right? You make them zeros. And in the fetch buffer, you will be having instruction, right? Make that instruction 0. So that now when they propagate also in the next clock cycle, because of these dummy instructions, nothing will happen. It is like flushing the instructions. Exactly like, did you remember? We did it when we were discussing load instruction followed by add instruction, correct? stall cycle. So here also we will be introducing stall. So finally, in one line I will tell you, whenever you realize, generally in the third clock cycle you can realize if you really want. Whenever you realize, immediately make the second instruction which is in the decode stage, simply make it 0. That means make all the control signals related to that decode 0 and make all the instruction, because at the same time in the fetch stage, see this entire thing is only one thing. See, I can show with vertical lines like this. Fetch, decode, execution. You are at execution stage, correct? In the execution stage you realized that there is a hazard immediately. So in the decode stage there is a buffer, right? Make all the control signals to zeros. Now in the fetch stage there is a buffer, right? Make all that, in the fetch stage buffer what you have, you will have instruction. Make that instruction 0. Okay. So what is the effect of that is, if this instruction fetch, whatever this instruction you have, right, 0 instruction, if it is moved to the next level in the next clock cycle, there will not be any problem, because so that will not have any effect on the logic. That's why. So they will be now later on this instruction, this fetched instruction will be moved to decode, decode instruction will be moved to execute. Okay, but still there will not be any problem. This concept is called flushing. Okay, finally we are flushing it. Sir, in the GATE exam what kind of question they ask? You should know one thing. So only one thing you should know. Finally, we are cancelling the effect of these instructions by making all of them to zeros appropriately. If you want to go into more details, I can explain, but generally for GATE it is not required. Now let us summarize. So this time in this summary you will be understanding everything clearly. So if you observe the 3 clock cycles, whenever there is a branch instruction, so you will be fetching the instruction, decoding and executing. By that time you will be executing the branch instruction. By that time mistakenly you will be fetching the second instruction, right, and decoding it. Sorry, you will be decoding the second instruction, and by that time you will be fetching the third instruction. Okay, when you realize that there is a branch success, then by that time you will be decoding one instruction, you will be fetching that instruction. To nullify the effect of that two instructions, we have to do flushing. So flushing is a circuit. Okay, we can do flushing by a circuit. What that circuit should do is, that should make all the decoded instruction to zeros. That means it should make all the control signals of decoded instruction to zeros. Already I explained that. Now apart from that, it has to make other instruction which is fetched to zeros in one glance. If it is done, then what happens, we will see in the 4th clock cycle. In the 4th clock cycle, this will go to memory stage, right, as usual. There is no problem. Since this is dummy instruction, nothing will happen. Okay, there is no effect on that. That's why it is called flush. Now in the 4th clock cycle, this will go to decode stage, but nothing will happen because this instruction itself looks like 0 for the circuit. Then it will not. See, we have to implement these things in a very serious way with all the details. But in the high level, we study like a story. Understand? Now the 5th clock cycle, if you focus, in the 4th clock cycle, finally this one is done. Now, sir, in the 3rd clock cycle, you have shown execution stage, decode stage, fetch stage. We understood. In the 4th clock cycle, you have shown us only memory stage, decode stage, execution stage, and fetch. Decode stage. What about fetch stage? In the 4th clock cycle, if you see, by that time we can update the program counter to write. Correct? Assume that in the execution stage itself we are updating the program counter. So the program counter shows 154 by that time. Then when you fetch the instruction, which instruction will be fetched? The instruction at 154, that is IK. So after that we know the story, because if really this is fetched in the 4th clock cycle, everything is going to be okay. Correct? Now we will see 6th clock cycle also. Okay. Now let me show 4, 5, 6 clock cycles. In the 4th clock cycle, what happens? Memory stage will happen for first instruction. Yes, it is correct. Now here what happens, we'll see. Instruction fetch 2, decode 2, execution 2, but since these are all nullified, there is no effect. Correct? nothing will happen, there is no effect. Now in the third clock cycle we fetched third instruction, but we made it nullified, that means we made the instruction 0, so that there is no decode effect. If you decode also there is no problem. In the fourth clock cycle, see, memory, execution, decode. In the fourth clock cycle, which thing will be executing? Fetching instruction fetch of 154, because by that time already program counter is 154. So IF, instruction fetch of kth instruction. Understand? Now in the fifth clock cycle, write back will happen for first instruction. Perfect, it should happen. So this memory stage will happen for this this second instruction, but no effect of that, already we nullified it. So it is like, you have a snake, okay, suddenly you have seen a snake analogy, and it is poisonous. Then what you realized is, if it goes, actually it should not freely roam in the world, because it's poisonous. Sometimes what can it do is, it can bite someone, right? Then what happens? So a lot of people will die. So how, but you don't want to kill the snake, you don't have chance also. Okay, let's say if you cannot kill that snake, what you should do? Simply hold it and cut its that poisonous thorns. So what happens if you do that? Then this kind of instruction will occur. Finally you are not disturbing the instruction, it's like a snake, it is going to next levels, but you disable all its power, so that it is not doing anything in the memory stage and write back stage, so there will not be any problem. In the sixth clock cycle, write back of second instruction will happen, that is dummy instruction. So in the fifth clock cycle, execution of third instruction will happen, again dummy, in the fifth clock cycle. In the fifth clock cycle, decoding of kth instruction will be done, it is right, it is right. Now in the sixth clock cycle, so what happens? This write back of, sorry, memory of the third instruction will happen, that is dummy. In the sixth clock cycle also, execution of k will be done, that is right. In the seventh clock cycle, what happens? So this is done. So now this is entirely done, this is entirely done. See, this will be going to write back stage of 3. Now here execution, then here memory of k. Perfect, no problem. In that way it will be continued. So finally I can say that it is like you are flushing these two instructions. After I instruction fetch 1, you will be rightly fetching only this kth instruction, but you wasted the time. That is what I would like to say. Finally control hazards are going to kill your pipeline's performance, right? So how many stall cycles you introduced? We supposed to, it is very easy to see. If someone asks how many stall cycles some instruction introduces, very easy. You supposed to execute instruction fetch of k here, ideally speaking, correct? But what you did? You did not do that. Here you wasted. This stage you wasted, this cycle you wasted, and this cycle you utilized. Then 2 stall cycles it introduced, because you realized the mistake in execution stage. If you have realized the same mistake in the decode stage, then we can say one more stall cycle, then that such kind of things only introduce one stall cycle, right? Now finally how many stall cycles are there here? 2, but by doing some optimization we can make it only 1. Sir, how, sir? Rather than doing the comparison, how did you know that branch instruction is successful or unsuccessful? By comparing R1 and R2, right? So what people realized is, most of the time that comparison is very fast, and it takes very less time. So if you can move that operation to decode stage, for that we have to build a new circuitry here. So decoder should have extra circuitry, that is comparator circuitry. Using that we do comparison in the decode stage also. So extra circuit, not this one, we are not sharing with execution stage. Then again what happens? Structural hazard will occur. So we are not sharing, we are having a new comparator here, brand new. Then we will be decoding, we will be comparing in the decode stage. Then immediately in the second clock itself you will know whether the instruction to be fetched is kth one or second one. But of course by that time already you fetched it, then only one will be wasted, only one cycle. That's why we say that by moving your this comparisons or comparator to second stage, we can reduce the stall cycles to 1 from 2. Understand? So this is a story about control hazards, but we have to learn so many things about this. So can we avoid these control hazards? We can't, because we can't guess when, without knowing, without seeing this branch instruction, how can you say whether it is successful or unsuccessful? Let me ask one question. In the C programming, let's say you have one condition, if condition. Let me ask you one question. That if condition is going to be, successful or unsuccessful, will you know? If I know that, why I write if condition? Try to understand. If really I know it while writing the code or executing, then why will I write it? Correct? So we write if conditions only if you have two cases or two possibilities. That's why. So here also branch instructions, whether it is successful or unsuccessful, nobody knows. That's why definitely control hazards will introduce stall cycles. We can't avoid, like data forwarding. Did you remember? We have solved a lot of our this data hazards by using operand forwarding, right? We did not introduce stall cycles so many times, but in that also sometimes we cannot avoid. But in control hazards also sometimes we can avoid stall cycles, but sometimes we cannot. Sir, when can we avoid stall cycles? If the branch won't take, that means if branch instruction is unsuccessful, then whatever you are fetching is everything is right, there will not be any problem. Correct? But branch is successful, then definitely it introduces stall cycles. Understand? Now, so there are some strategies actually to take the right decision to reduce the stall cycles. How to reduce the stall cycles is the open question. For that we have some of the strategies, we will be studying that. Okay, let us study that strategies.